Thank you. Good morning. Last time we were about halfway through this section on monolithic refractories. We went over some background information, and then we were going over the raw materials, and we were about a little bit more than halfway going through the different kinds of binders. We went over the calcium aluminate cements, the hydratable aluminas, and then one of the phosphates. So just to finish up the binders, we have the alkali silicates and then the some colloidal silica. And when I finish that, we'll look at uh, some processing of these materials, a few microstructures, and some key properties. So the alkali silicates, they just form a very viscous liquid when they're dissolved in water. And this is the formula for the sodium silicates. Na2O, then Y, SiO2, and ZH2O. So the ratio of Y to Z, which is the ratio of the silica to the water, determines the type of silicate that forms. So a 0.5 ratio is an orthosilicate, a 0.67 is a pyrosilicate, and then a 1.0 is a metasilicate. 2 to 4.5, those are the non-crystalline silicates known as water glass. So these are the ranges that are used to make a refractory, a monolithic. So basically what happens when they form a gel, they form this chain-like structure. So you have an SiO-Si bond, and then bonded to the Si is an OH group and an ONA. So you're forming these chains that form the gel. So at room temperature, the water glass forms an amorphous gel. And then when you heat it up between 600 to 700 degrees C, the gel starts to crystallize. But on further heating, it's a low temperature material. So temperatures greater than 900 degrees C, you start forming a liquid. So these types of binders are used in basic castables or for making an acid-resistant aluminosilicate castable. And then the colloidal silica is a dispersion of nano-sized silica particles in water. So these fine silica particles are very reactive, so that they improve the bonding and densification because they center at low temperatures. So the finer the particle size, the more reactive, and that allows sintering at lower temperatures. There's no chemically bound water, so they're in a water suspension. So once you reach 100 degrees C, the physically held water is gone. So there's no dry out to be concerned about because there's no chemically bound water. So here's some examples of colloidal silica. The first number in percent is the solid content. So there's mixtures here at 30, 40, and 50 weight percent silica. The second number, 8, 14, and 80 is the average particle size in nanometers. So you can see 8, 14, 80 in nanometers for the particle size, and then 30, 40, and 50 for the weight percent SiO2. These three give the surface area, and then the stabilizing agent in 4 of the cases is sodium, and in 1 case, it's ammonia. So these charges on the colloidal silica just keep them in suspension. So the silica particles are uniform spheres, and their internal structure consists of siloxane bonds, so SiO-Si bonds internally, And then the surface of these particles, the surface layer is comprised of silanol groups, SiOH groups. So during this process where the material dries out, the physically held water is removed, the silanol groups on the surface, the SiOH groups, they condense, they split off water and form the SiO siloxane bonds. And that provides shrinkage and strength by the type of bonding that's formed. So this is just a schematic diagram of the reaction. So the dark circles here with the Si are the silicon particles, and they have OH groups on this attached to the surface. So here's two particles with their OH groups coming together, and they split off water and form an SiO-Si bond. And then eventually they all start forming this SiO-Si bond, and eventually they'll form a three-dimensional network that looks something like this. So the OHs combine, split off water, and form the SiO-Si bond, and that gives rise to the strength. So colloidal silica has a couple advantages. You can put it together with reactive alumina or reactive MgO. So just fine particle size alumina or fine particle size MgO. So when you have a silica with alumina, it's going to form mullite. And we've seen this reaction before. Alumina plus silica forms mullite, which is 3Al2O3, 2SiO2. And if you have reactive fine particle size MgO, it forms phosphorite. So MgO plus SiO2 forms this magnesium silicate, Mg2SiO4. Both mullite and phosphorite are fairly high temperature refractory materials. So we'll look at each type of monolithic material. The first is a castable mix. These are simply produced by combining the appropriate aggregates, the appropriate matrix components, any additives, and the type of binder. And these are put together at different ratios to obtain different properties for different applications. So castables are supplied in dry form, and they have a limited shelf life. They can absorb water from the air and react. So they have a limited shelf life. I think the minimum shelf life is usually going to be at least a half a year. And on-site castables are mixed with the liquid, typically water, and then they're cast into some type of mold, and then they're cured. And we looked at the different type of calcium aluminate cement reactions for the curing process. So the mixing just depends on the scale. Usually on a smaller scale, there's a paddle type mixer or a cement mixer. Or maybe a larger scale might be an auger or a pug mixer. So the particle sizing is important. Castable mixes, their size or proportion to achieve a desired particle size distribution, which controls the packing density, which again controls the porosity and the strength. The particle sizing is kind of critical because it affects the rheology during installation. And again, after drying, it controls the final density, the porosity content, and the strength. So there's two basic ways of putting together a castable, a random system for sizing and particle packing, or an ordered system for sizing and particle packing. The ordered system has two versions. One is gap sized and one is continuous sized. So the random system, aggregates are just sized in very broad size distributions. They're blended with fillers or modifiers. That would be the matrix material or any other chemicals to modify it. And that just produces adequate particle size distribution that gives somewhat reasonable rheology and flow properties and reasonable physical properties. So this is a not a very controlled particle size distribution. So for conventional castables, we're looking at maybe 8 to 15% water during the casting process, and the porosities are going to be pretty high, 20 to 30%. What's more typical are gap sized and continuous size particle size distributions. So when you go to these ordered systems, you're going to reduce the water content. You're going to have better control over the rheology. So you may have a system that requires vibration that's thixotropic, so the shear stresses from vibration cause material to flow, or you can adjust the particle size distribution so it's more of a free-flowing or self-leveling material. So order systems minimize porosity, they maximize particle contact for improved bonding, and they're going to optimize the strength. So we'll look at each one of these. Gap sizing is going to be a mixture of 2, 3, or 4, or even more particle size distribution. So these are going to be tightly graded aggregates. So these are very tight particle size distributions, and they're put together to achieve good packing. So you start out with a coarse particle, and you pack those, and then there's a void space. So you put the next size particle in that void space. That in turn creates more void spaces, much smaller void spaces. So you pick a third particle size that fits in those void spaces. So that's basically gap sizing. Gap sizing, the rheology, is very poor for flow behavior. They're tightly packed, but you're going to need a great deal of vibration to place these materials, but they're going to have very low water contents, 3 to 5%, and they're going to have minimum porosity, maybe 10 to 15%. So when you make a gap size material, it's going to have poor flow behavior. You're going to need to probably vibrate it, but you're going to have good physical properties because you minimize water content and porosity. The other approach is a continuous size material. So aggregates are added in relatively large number of closely spaced size fractions to make a more continuous distribution curve. So this is percent undersized from 1 to 100 on a log scale. And then this is the particle size diameter in microns. So from maybe 0.1 to 10,000 microns. So you have this continuous size distribution. It's not gap sized. So that gives good flow, good rheology type properties. You're also going to minimize water contents. You're going to minimize porosity. And you're going to have maximum density. So you're going to have good physical properties. So both gap sizing and continuous sizing give good properties, but the continuous sizing is more desirable for easy placement. So these castables, you can make any dimension, any orientation, depending how you put the molds in place. So you can make a floor of a furnace, a wall, or a roof. You're usually casting against the shell of a vessel, the metal or steel shell. That's going to be part of the mold. You're going to put an additional mold material in there to create a wall or a roof. Metal anchors are commonly used to secure the castable to the wall or the roof. And they're usually vibrated. That produces better density, which decreases the porosity and increases the strength. If you adjust the particle size distribution properly, you may not need vibration. So this just illustrates the different orientations for the castables. Number one here, there's a metal shell, and then welded to that shell are these metal anchors. They're usually stainless steel. So you'll have a mold material, and then you can cast the wall in place with the metal anchors securing the wall to the shell. Number two here is a combination of ceramic anchors and metal anchors. One of the problems with a metal anchor, it's going to oxidize at high temperatures. But a ceramic anchor looks something like this. These are usually 4 to 6 inches in cross section, and then they have these ridges in them to lock in the castable. So there'll be the thickness of the lining, and you can see after the lining is cast, you can see the refractory anchors. So these are fired refractories. Here's an example going around a bend here from a ceiling to a wall with anchors in place. And then this is just showing a furnace roof, and the anchors are suspended from these rails. So here's your ceramic anchor, and here's your metal anchor. And then this one here, number 5, there's this metal mesh that's hex steel type anchors. And then the castable is just cast into this metal mesh. So these are usually thin wall linings, maybe boiler type applications where there's probably extensive water cooling on the cold face. So those are just different ways the castable can be put in place. Here's an inverted roof. You can see the ceramic anchors, and they're pouring in the castable, and this roof would be turned over and put in place. There's this man here standing on the edge and on an anchor. To me, that looks like he's got a safety issue. Anyway, after you place the castable, it sets and hardens. We looked at the different types of cement reactions for the different temperatures. So you have to dry out the castable. There's physically held water in the pores, and then the chemically held water. So this step is usually done very slowly because if you do it too fast, you'll build up steam pressure, and that will disintegrate the lining. So the dehydration of the calcium aluminate cement or the hydrated alumina, the AH3, must be done slowly without building up any steam pressure. The steam is going to escape through the open porosity. However, if you heat it up too fast, the steam is not going to escape fast enough. It's going to build up very high pressures. Mild cases might be spalling of some of the refractory lining. Extreme cases would be an explosion. And these can be quite violent and quite dangerous. So you have to be really careful. These low cement castables are designed to be pretty dense. So that's going to make more issues when removing the water. So you can add organic fibers. So these fibers decompose at a lower temperature than the dehydration temperature. So the cement has a certain dehydration temperature. We looked at those. So they're going to decompose and leave a void space, and that's the pathway for the steam to escape. So fibers are going to generally burn out less than 200 degrees C. And fibers can be 15 to 40 microns in diameter and maybe 3 to 10 millimeters in length. So they may be polypropylene, an acrylic-based fiber, or a polyester-based fiber. So they're going to burn out and leave a void space for steam removal. So you can measure the permeability of a refractory, and it's just the ability of the refractory to transmit a fluid or a gas. So the higher the permeability, the easier it is to remove the water. So the dehydration rate is going to depend on the permeability. So here's a graph of permeability, and the units of permeability are centidarcies versus temperature in degrees C. So the top curve is a conventional high cement refractory. So that one's going to have the highest porosity, to have the most water to be removed. So that's a pretty permeable material. But here's a low cement castable, the bottom curve. Um, these are usually designed for high density. So it has very little permeability below 600. Then it starts to increase as the water comes off. And then the dotted line in the middle is the same low cement castable, but has organic burnout fibers. So you can see the effect of the fibers is to shift the permeability up. It's not going to be anywhere near the conventional material, but it's going to be better than having no fibers. The plastic mixes, the first plastic mixes were made with clays, low alumina silicate clays. And when mixed with water, the clays become plastic so that they provide good deformation characteristics. And they adhere very well. So the plastic mixes, again, have a wide range of compositions, depending on the type of aggregates and fines. Bonding agents originally were clays, but they can also be phosphates and various types of resins. These are pretty much delivered in the wet stage. They're in the form of dense compacts. They're usually on the order of a cubic foot. So they're not compacted as much as ramming mixes, but they're delivered ready to use in a dense plastic state. So these plastic mixes are applied layer by layer by using a ramming tool, hydraulic ear-type hammer, and they can be built up to thicknesses on the order of 3 feet. So these blocks that I mentioned, usually about a cubic foot, are placed in rolls and rows, and then they're tamped together to form a continuous lining. They have an initial water content, and that tends to lead to higher porosity after drying than a ramming mix, which is delivered in powder form. So here's a tool. You can see the pieces of the plastic refractory. It's just being rammed into place. So it is densified somewhat during this process. The ramming mixes are also densified by using a compacting tool, a pneumatic compacting tool. But the ramming mixes are usually dry or maybe slightly wet. So they're loose powders. They're not in these plastic masses. So the binding agents can be clay, maybe an organic resin or phosphate, silicates, or even a tar or pitch. And this loose powders for the ramming mixes, usually you place a furnace floor with these. It's easy to place a floor with loose powders. It's not easy to place a wall. So they're usually used in the furnace floors. So you spread out a thin layer, 2 to 8 inches, then you compact it, and it usually compacted about 50% of its thickness. You're shearing the mixture with this pneumatic hammer, and you compact the layer, you add a second layer and you compact that, and you keep doing that until you build up the thickness you need. So ramming can give pretty dense shapes, denser than plastics. And again, these have to be dried out carefully. So do the plastics. Here's a pneumatic hammer, um, just densifying a ramming mix. The gunning mixes, they can be used for quick repairs, or they can just be used to build up a lining. Quick repairs most likely would be done during an operation, so they'd probably be hot repairs. So because of the way these are gunned onto a surface, gunning mixes are not going to be as good as other monolithics. They're not going to be as dense, so their properties are going to be inferior. However, it's very easy to install a lining with a gunning mix. It's a quick installation. Also, it's a quick repair, whether it's a cold repair or hot repair. And the quality of any gunning lining or even a shotcrete lining is going to depend on how good the operator is. So you need an experienced person doing the installation. So in any gunning mix operation, you have your dry solid particles. They're pneumatically driven by a stream of high pressure air. And then at the nozzle, you have jets of high pressure water that mix in with the dry particles. So gunning mixes are applied using a mixing chamber. They're fed by a pneumatically driven stream of dry solid particles. And then at the nozzle, there's jets of high pressure water. So it's inline mixing. At the nozzle, the wet solids pass out of the nozzle, impact the wall, and adhere to the wall or a ceiling or a floor. Dry and semi-dry gun mixes, you try to use a minimum amount of water. The solids can be slightly pre-moistened, and I mentioned you can gun onto a hot surface. So you can do a hot repair as well as a cold repair. So gunning mixes usually have clay binders, silicates, colloidal silica, phosphates, the calcium aluminate cement, or maybe some type of organic compound. Molasses is listed here, lignosulfates, maybe some type of resin. And with all of these monolithics, the aggregate composition, the matrix composition are going to be determined by what the application is. Gunning mix, the disadvantage is something known as rebound. So materials that are not completely wetted may rebound off the surface, and then you have wasted material. So how efficient a gunning operation is going to depend on the amount of rebound. And again, the rebound is just material that bounces off the wall or the ceiling. So it's lost material due to non-sticking collisions of the sprayed particles on the lining. So rebound is controlled by the particle size and the adhesion by optimizing the binder system. So larger particles tend to bounce off the wall or the ceiling, whatever you're gunning. So large particles do not tend to adhere as well. So the maximum particle size in a gunning mix is usually 5 millimeters. Bigger particles tend to rebound. Fine particles are deflected to the airstream, and they're not attached to the wall. So particles less than 40 microns are not desired. So if the particles are too large, they'll bounce off the wall. The particles are too fine, they may not reach the wall. So if you can do an installation with less than 5% rebound, that's a pretty good job using a gunning mix. Here's a cylindrical type lining, probably a rotary kiln. You can see the anchors are welded to the metal shell. And over here, this lining, probably maybe a foot thick, is gunned into place. So this would be the next part of the lining that's gunned. Shotcreting is similar to gunning, but the material is pre-mixed with water instead of being mixed at the nozzle. So a large batch of castable is mixed with the correct amount of water, and it's charged into a pump. And then a special nozzle mixes the castable, and as it mixes in the nozzle, there's usually going to be an addition of an activator or accelerator that's going to accelerate the curing process. So these additives increase the rate of hydration of the calcium aluminate cements. And so this is shot onto a lining surface, and you build up the amount of material to whatever thickness you want. Here's a shotcreting example where the wet mixture is shot onto a wall. So those cover some of the different types of monolithics and how they're installed. Some microstructures, and this is a calcium aluminate cement bonded monolithic refractory. So some of the generalizations concerning the microstructure, at room temperature, you're simply going to have aggregates, the fines in the matrix, the hydrated cement, and then physically held water. So as you heat this material up, and we're looking at temperatures less than 315 degrees C, you're going to have the aggregates, the fines. You're still going to have the hydrated cement, but you've driven off the physically held water, so you can have porosity. So then at higher temperatures greater than 315 degrees C, you're going to still have the aggregates, the fines. The cement phases will be crystallized at this point. You're going to have porosity. And if you go high enough in temperature, you're going to initiate sintering processes, whether they're solid state or liquid phase sintering. If they're liquid phase, you'll have some liquids present. So this is a calcium aluminate cement material. The gray angular type regions are a crushed high alumina. And you can see they're fully dense, so they're probably a fused cast alumina. So here's a coarse material, here's some porosity, and then you can see the finer materials in the matrix. And then between these alumina fines is the matrix where the calcium aluminate cement is. This one has some bright spherical particles. These are metallic particles. They're probably an antioxidation agent. So this is probably a high aluminum material. And in the matrix, besides the calcium aluminate cement, there's probably carbon. That's why they have these spherical particles to protect the carbon. This is a gunning mix. Again, it's based on calcium aluminate cement. This gunning mix appears to be designed for good corrosion resistance. So you'll see a silicon carbide particle over here. The bright particles are zirconia. So those are there to enhance the corrosion resistance. You also have high alumina. particles, and you can see a second phase in here, probably a glassy phase, the lighter gray. And then the very fine matrix where you have the calcium aluminate cement. So this one has silicon carbide, high alumina, and zirconia for the aggregates and the fines, and then the calcium aluminate cement. So when you have a calcium aluminate cement bonded material, we can make some generalizations for the properties. At room temperature, the properties are going to be determined by the type and amount of the hydrated cement phases present, how much water was used, and the water cement ratio. What's important is the aggregate to cement bond. So the less water you use, the less porosity, and you have to develop a cement to aggregate bond to give good strength. Then at high temperature, once the material is fired, again, the aggregate to cement bond is going to determine the strength properties. So I have a few of these property data sheets. This is for a conventional cement castable. So it's a high cement castable, and it goes from about 45 to 95% alumina. And all I want to do is point out what happens when you heat these materials. So this is the cold MOR in megapascals. This is the cold crushing in megapascals. And these are measured after heating to these temperatures. So 110 degrees C is basically drying out the material, removing the physically held water. 815 degrees C is you've already destroyed the hydraulic bonds. And then 1370 degrees C, you start the sintering process. So what I just want to point out here is if you look at 815 degrees C for the cold MOR, you can see it's lower than at 110 degrees C. But then at 1370, when the sintering process starts, it starts to increase again. So the intermediate temperatures, these materials are weak when the hydraulic bond is destroyed. And the cold crushing follows the same pattern. You have a loss of strength at the intermediate temperature. And then when you go up to a higher temperature, the materials start to get stronger because of the sintering process. So these are measured at room temperature. But what's probably more important is the high temperature strength. So at 815 degrees C, it has a certain strength. Not all that different than 815 degrees C measured at room temperature because you have destroyed the hydraulic bonds here. But at the higher temperature, the lower purity materials are going to have lower strengths. This one maintains the strength because it is a high purity material. So you're probably forming a liquid phase here, which lowers the strength. Percent linear change is always measured on these materials. These are pretty low numbers. A little negative means a slight shrinkage, positive means a slight expansion. But there's not a big change here after firing to those temperatures. So if you look at hot MOR and cold MOR, both in megapascals versus temperature. So cold MOR would be fired at these temperatures and measured at room temperature. Hot MOR, you're bringing the material up to these temperatures and measuring at temperature. So you can see the cold MOR, there's a loss in strength where the material dehydrates. And then when it starts to sinter, whether again, it's solid state or liquid phase sintering, when you measure it at room temperature, you're going to see a strength increase. But the hot MR will usually decrease at some point because of liquid formation. In this case, it's probably an orthite, which is Ca S2, C is calcium oxide, A is aluminum oxide, and S is SiO2. So these have low melting eutectics, so the hot MOR will decrease. So cold MR is a good measurement to make for quality control, but it really doesn't tell you what's going to happen at use temperatures. This is hot MR again in megapascals versus temperature. And these are again conventional high cement castables. This top curve is a 95% alumina with tabular alumina aggregates. The next curve is 70% alumina with mullite aggregates. The curve below that is a super duty refractory with high purity. CAC is calcium aluminate cement. And the bottom curve is super duty, but it has a low purity calcium aluminate cement. So you can see that the strength loss here um, due to dehydration of the cement. Um, Sintering takes place, and then the strength tends to increase. This one stays high because it's very high purity, but these other three start to decrease um, because you're probably forming an orthite, the CAS2 compound, which with the low melting eutectics. This is high purity, so you're probably forming Ca6, which is a high temperature phase. And another data sheet for a low cement castable. And these are from 60 to 90% alumina. There's a bulk density here, cold MOR, cold crushing, and hot MOR. So just pointing out a few features here. If you look at the intermediate temperatures, you're not seeing a strength decrease, whether it's cold MOR or cold crushing. So low cement castable, you're not really dehydrating and destroying a cement phase. So you usually have a reactive component in there to provide the bond, whether it's a silica or an alumina. So the strength is actually increasing at this intermediate temperature and holding at the higher temperatures. But again, cold MR and cold crushing are good for checking properties, especially quality control type properties. But if you look at the hot MRs, they're good at 11, about 1100 degrees C, but then depending on the purity, they start falling off. The lower the purity, the lower the strength. So this is a low cement castable. This is hot MOR in megapascals versus temperature. So this is a 70% alumina, no cement. So this is a mullite material. This solid curve here is the 70% alumina, low cement with a mullite aggregate. The dashed curve here is another 70% alumina, but it's an ultra low cement castable with mullite aggregate. And then this is a super duty low cement with a fire clay or flint clay aggregate. So in all of these, since they're trying to produce mullite as the bonding phase, there's a increase in strength above 1,000 degrees C. So that's where the mullite is forming. These are low cement castables. They're most likely going to have a fumed silica that reacts with the alumina for mullite. So that improves the strength. And eventually, as you go up in higher temperatures, you start forming liquids and the strength will fall off. This is another low cement castable, hot MOR in megapascals versus alumina content. And in this region here, about 75% alumina. These measurements were made at 1370 degrees C. This is where you form your maximum mullite content, and that's where you're going to have your maximum strength. Remember, mullite forms those interlocking crystals, that needle-shaped crystals that give good strength. Again, a low cement castable, and we're looking at creep resistance or deformation percent. So 0 to 1.6% deformation. So the higher the deformation, the worse the creep resistance. And number of hours at this temperature, 1425 degrees C. So creep tests are normally run at 50 or 100 hours. So the solid curve is a 65% alumina. The dotted curve is a 60% alumina. So this is just showing the higher the alumina content in a low cement castable, the better the creep resistance. This has less deformation than this dashed curve. So this is a comparison of different castable mixes for the creep. So deformation percent goes from 0 to 7. So here we have a conventional brick, a conventional high cement castable, and then a low cement castable. And these creep measurements were done at 1425 degrees C. So this open bar is a Super Duty aggregate, and then this cross-hatched bar is a 60 to 70% alumina, and then the darker cross-hatched bar is a higher alumina content. So for those three materials, these are the amount of deformation probably after 50 hours of creep. And you can see the conventional castable is worse than the brick. But then when you look at the low cement castable, it's actually better than a fired brick. So its creep resistance is really good because it's designed with low cement, which really reduces the amount of liquid phases that can form, and probably very good particle packing for high density. So the, these cements have replaced bricks to a large extent because you can achieve better properties in a castable than in a fired brick in some cases. The phosphate bonded materials, these are plastics, and just another data sheet going from about 40 to 90% alumina, and this one is an 80% silicon carbide plastic. So we have cold MOR, and then finally hot MOR, and PLC is a percent linear change. You want those to be as small as possible. So you can see at this intermediate temperature, we're not losing any strength because of the phosphate bonding. And the strength is continuing to increase as you increase the temperature. And even at high temperatures, 1370 degrees C, you're still retaining a good deal of strength because you're forming this phosphate type bond. And I just put in a ramming mix with a phosphate bond. And if you look at the cold MOR and the cold crushing, this is the cold crushing. It holds its strength, and same thing with the cold MOR. So you're not dehydrating a cement like in a castable. So you're maintaining the strength throughout the temperature range. And again, you want minimum change in dimensions. And then I put in a gunning mix. So this gunning mix is based on a calcium aluminate cement. So we're going from 45 to 90% alumina. And the cold crushing strength, there's some decrease at the intermediate temperature. And you can also see the decrease in the cold MOR. Again, you're dehydrating the cement, you're destroying the cementitious bond, you're creating porosity. That's going to lower the strengths. And then the hot MOR, these are all going to develop, in this case, at 1370 degrees C, a liquid phase. So they're all going to decrease in strength. So again, a hot MOR is much more valuable than the cold MOR, cold crushing, because it's going to tell you exactly what's going to happen at high temperatures. And then this is a shotcrete mix, again, based on a calcium aluminate cement. And they're going from about 50 to 95% alumina. So there is, if you look at the cold MOR and the cold crushing, there may be slight decreases here, modest strength losses, but these are denser materials because of the shotcreting process. So they're maintaining their strength a little bit better than for a gunning mix. And again, the percent linear changes are not that big. And these are pretty good porosities after firing at 815 degrees C. They're not that bad. So shotcreting is better than gunning in terms of providing a higher density. And the last slide here, um, I'm just comparing a shotcrete with a dry vibratable. And these are low calcium aluminate cement materials. So this is a vibratable and this is a gunning mix. It's sprayed, so it's a shotcrete. And they're both pretty high alumina contents, so they're not that different in chemistries. And they're producing pretty low porosities at 815 degrees C, about 14%. So the dry vibratable is actually outperforming the sprayed material. It has no water. It's vibrated into place to form a dense lining. And then there's a additive to promote the sintering. So you can see the dry vibratable is actually superior to this shotcreted material. And then the percent linear change should be small. So these dry vibratables usually used to line induction type furnaces, and they're cured when you heat up the furnace, and that's when the sintering takes place. And because of the lack of cement and the lack of water, you're going to form denser materials and they're going to be stronger. So that's what I have on monolithic materials. Um, there's no class on Wednesday, so I'll see you in another week. And I think the next class we start looking at how you design refractories and followed by different applications. And in those applications, I'm going to put together quite a few microstructures of used materials so we can compare what happens during use in different applications to the microstructures. So have a good Thanksgiving, and I'll see you in about a week. Again, thanks.